afternoon everyone. So, we saw that in the last lecture we ended the last lecture on the discussion on discrete wavelet transforms. Namely, we introduced discrete wavelet functions using the definition of continuous wavelet functions. And towards the later half of the last lecture we saw how the fact that if these wavelets are orthonormal, then in that case the wavelet transforms for the discrete cases are well defined. So, today in this lecture I am going to describe three different types of discrete wavelet transforms, namely the Haar wavelets, the Shannon wavelets and the Dobbechi wavelets. Okay, so, let us move on. So, let me just again briefly recap what I just said. So, what I saw was my definition of psi mn, which was defined to be of the form. So, psi mn of x, which was defined of this form a 0 to the power m minus m times psi of, so a 0 to the power minus m by 2. So, recall this definition here. So, a 0 to the power minus m by 2 times psi a 0 to the power minus m times x minus n times b 0. So, this definition makes sense. It makes sense if I have that my psi mn's are orthonormal. Okay. So, that is the conclusion that we saw in my last lecture after the discussion on the definition of frames. So, if I can show that my discrete wavelets by these definitions are orthonormal, not orthogonal, but orthonormal, then this particular definition from the continuous wavelets, it makes sense. Okay. So, whatever discrete wavelet I define, all I need to make sure is that those particular wavelets are orthonormal. Okay. So, let us look at some particular example here. So, what I have is, before I move ahead, let me define what are orthonormal wavelets and how should I look for orthonormality, orthonormal wavelets. Okay. So, a wavelet is orthonormal, a wavelet defined by all those square integrable function is orthonormal if the family of functions psi mn generated by the continuous wavelets psi is given by the following definition: psi mn of x is 2 to the power m by 2. So, now note that I am using my a 0 to be half and I am using my b 0, my b 0 will be 1 in the definition above. Okay. So, if I have this particular definition, psi mn is 2 to the power m by 2 times psi of 2 to the power m x minus n, then corresponding to this continuous wavelet, my discrete version of this wavelet will be orthonormal if I have that the following inner product psi mn with psi k l integral from negative infinity to infinity psi mn of x psi k l of x dx. This particular integral is the product of the following two delta functions, delta of m comma k times delta of n comma l for all integers m, n, k and l. Okay. So, for all integers m, n, k and l. Okay, so if that happens, then I have a family of orthonormal wavelets, discrete orthonormal wavelets. Okay, and if that happens, then my wavelets are well defined. So all I have to worry about is find the orthonormality of the wavelets that I define. Okay, so let's, before I show some examples, let's look at a quick result. So let me introduce a short result in the form of a lemma. So the result says that if psi and phi are two square integrable functions, then the inner product of m comma k with n comma m comma l, this inner product is also the inner product of n comma k with phi of n comma l. Okay. So basically, which means that we can replace the indices if phi and psi are two square integrable functions. So the proof is quite straightforward. We see, let us look at the left hand side of the statement. I see that the inner product of these two square integrable functions psi m k phi m l will be defined as, by the definition of psi and phi, is defined as integral negative infinity to infinity 2 to the power m by 2 times times square, because both has a factor 2 to the power m by 2 sitting outside the definition, times psi of 2 to the power m x minus k times phi of 2 to the power m x minus l. Okay, and the integration is with respect to x. I see that if I assume if I do the following change of variables, notice that I need to show that the index m can be replaced by another index n. Okay, so if I assume that my 2 to the power n, 2 to the power m x, so this particular index is 2 to the power n t. Okay, so I am replacing my variable x with my variable t with this choice of replacement. Okay, so I see that this integral becomes from negative infinity to infinity. So 2 to the power m by 2 square, which is 2 to the power m. Well, after replacing, I get 2 to the power n. So 2 to the power m dx is 2 to the power n dt. So 2 to the power n dt psi of 2 to the power n t minus k times phi of 2 to the power n t minus l. Dt is already taken care of. I see that, so that is after this following replacement. I see that this is nothing but the inner product of psi with the index n and k with the inner product of phi with the index n and l. Okay. So that's the index. So that is my right hand side, and hence the result. Okay. So then let's start with the definition of a discrete wavelet, namely the Haar discrete wavelet. So the discrete Haar wavelet case. Okay. So let us look at, now as we have shown here, the continuous version is a very simple function. Even the discrete version is the simplest of the discrete case that we can look at, the simplest case. Okay. So namely, so now let us now consider the following continuous function. So I am going to call this as my scaling function. Consider the following scaling function phi to be given as the characteristic function on the interval 0 to 1. I know that this characteristic function by definition is 1 if x is from 0 to 1 and 0 otherwise. Okay. So, my characteristic function is defined as follows. Well, notice that this is well, see, this particular characteristic function is by definition is going to satisfy the following equation or the dilation equation. Okay. So, what I have is that this phi of x is going to satisfy my following summation, my following series phi of x given by square root n 2 times n negative infinity to infinity C n phi of 2 x minus n. Okay. So, phi is, if we were to consider this phi is a bounded square integrable function, if this is my choice of the wavelet, then phi must necessarily satisfy the corresponding series for the discrete wavelet transform. Okay. So, namely phi must satisfy this particular relation that is highlighted here, or so this means that my coefficients C n will be the integral square root 2. If I were to invert this relation, I get back my coefficients in the form of an integral. This is integral from negative infinity to infinity times phi of x times phi of 2 x minus n dx. Okay. So, that is how my coefficients are calculated. Now, the fact that phi is just a characteristic function over this interval 0 to 1, I can readily calculate these coefficients. Okay. So, what I get is the following. Since I have that phi of x is nothing but the characteristic function over 0 1, I see that my psi, my C functions, the coefficients can be readily calculated. My C 0 and C 1 comes out to be square root 1 by 2, and my C n's are 0 for all n greater than 1. Okay. So, then if I were to substitute, let us say, let me call this as 2. If I were to substitute 2 in this expression in my dilation equation, let me just recap that. My equation is phi of x given by square root 2 times summation C n phi of 2 x minus n. Okay. So, if I were to substitute all these values of C in this dilation equation, I see that I get the following result. I see that phi of x is given by is equal to phi of 2 x plus phi of 2 x minus 1. Okay. So, which means, notice that we have the following result now. I have shown here that phi is the linear combination of its odd and even translates. Phi is the linear combination of its odd and even translates of phi of 2 x. Okay. So, we see that the function phi here has been broken down into its even translation and the odd translation. Namely, if we were to draw these three functions, let us see how it looks like. So, I know that phi of x, my phi of x is a characteristic function. So, which means that my phi of x will be 1 from 0 to 1. Okay. And if I were to draw phi of 2 x, I know that phi of 2 x will be 1 from x from 0 to half, and it will be 0 from half to 1, okay, by this choice of argument. Similarly, phi of 2 x minus 1 is 1, well, it will be from 0 to half it is 0, and from half to 1 it is 1. Okay. So, I see that phi of 2 x becomes 1 in in half of this interval, and in the other half phi of phi of 2x is 1 in one half, phi of 2x minus 1 is 1 in the other half of the interval. Now, which means that my Haar wavelet, if I were to describe my Haar wavelet psi of x, then that would be nothing but phi of 2x minus phi of 2x minus 1. Why? Because I know my Haar wavelet is 1 from 0 to half, and it is 1 from, well, it will be minus 1 from half to 1 for the other half of the interval. Okay. So that's my Haar wavelet in terms of the scaling functions. Okay. So then let us well, I can always express this in this form. I can express this in terms of the characteristic function. So, it is from 0 to half it is 1, and from half to 1, this is minus 1. Okay. So, my characteristic function is, well, in terms of characteristic function, that is my continuous, well, that is the continuous version of the Haar wavelet. Okay. So, now let us look at the discrete version of this wavelet. Okay. So, for any integer, say for any m n which is in Z, let us consider the discrete Haar wavelet. Okay. So, let us start constructing the discrete Haar wavelet. So, I described my psi m n of t is 2 to the power negative m by 2 times psi of 2 to the power negative m t minus n. So, where my psi is the continuous, my continuous version of the Haar wavelet that we know of. Now, which means if so instead of my argument t, now I have the argument 2 to the power negative m t minus n. So, which means my region where the wavelet is 1 or minus 1 also changes due to this new argument. So, which means that this is also equal to the discrete Haar wavelet is this following this quantity, this scaled value with the corresponding signs. So, this is 2 to the power negative m by 2 in the region from t from 2 to the power m times n to t from 2 to the power m times n plus 2 to the power m minus 1. Okay. So, then if I see that this is also negative value of this amplitude, this scaling function, negative 2 to the power negative m by 2 from the region 2 to the power m times n plus 2 to the power m minus 1 until t from 2 to the power m times n plus 2 to the power, well, 2 to the power n. Okay, and otherwise it is 0. So, this definition of the discrete version of the Haar wavelet follows from the continuous version, from the regular continuous version that we are familiar. Okay. So, students are requested to check that the L2 norm of this discrete Haar wavelet is the same as the continuous Haar wavelet, the L2 norm of the continuous Haar wavelet, and also requested to check that this norm is equal to 1. So, which means that the discrete Haar wavelet is a square integrable function. Next, I have to see whether these wavelets are orthogonal or not. I have already shown you that these wavelets have a norm of 1. Okay. So, that is left as an exercise to the students. So, this question is, are these discrete wavelets orthogonal or not? Otherwise, the definition may not make sense. So, if they are orthogonal, we are fine. So, let us now consider the inner product of these discrete wavelets. So, let us consider the inner product. Okay, so let us consider the inner product of the wavelets psi of n comma m with psi of index k comma l. So, I know that this is also equal to the integral from negative infinity to infinity 2 to the power m by 2 psi of 2 to the power m times x minus n times 2 to the power k by 2 times psi of 2 to the power k x minus l dx. Okay, so then if I were to replace again, if I were to use the same replacement that we did for our lemma, let us replace the argument of one of the wavelets, that is replace 2 to the power m x minus n by t. I see that this is also equal to the integral of k minus m by 2 times integral from negative infinity to infinity times psi of t times psi of 2 to the power k minus m by k minus m times t plus n minus l dx. Okay. So, t plus n minus l dt. So, that will become dt because I have the new variable t. Okay, so, then this integral can now be looked at for two different cases. The first case could be when k is equal to m, and in that case I will show that this integral reduces to 1. And in the second case, if k is not equal to m, I will show that the integral reduces to 0, and hence we will show that this particular inner product is these inner product of these two wavelets are orthonormal. The wavelets are orthonormal. Okay, so let us look at the two cases. So, the first case is when I have m is equal to k. I see that if I were to consider psi m n inner product with psi m l. So, I have already replaced k by m here. So, in that case my factor of 2 to the power k minus m is 1, and I am left with the following integral psi of t psi of t minus l minus n, all the factors of 2 to the power exponent they cancel, dt. Okay. Notice that since I have that psi, my psi of t is already a Haar wavelet. So, psi of t is psi of t is 1 when t is from 0 to 1, and psi at the other function psi of t minus l minus n is 1 if t is valid from l minus n to l minus n plus 1. Okay. So, I see that why, because these are nothing but the characteristic functions. Okay. So, I see that due the way we have defined my function psi, they take values equal to 1 at these respective intervals, and notice that these two intervals, the intervals coincide if and only if I have L is equal to n. Okay. So, the intervals coincide only when, and the intervals will be 0 to 1 only when L is equal to n. So, which means that my integral, my inner product of psi mn with psi ml is nothing but the delta function L comma n, and hence I have shown that this is equal to 1 if L is equal to n. Okay. So, now let us look at the case when k is not equal to m. So, the second case when k is not equal to m, let us now assume, we could either have k less than m or k greater than m, but let us now assume without loss of generality that my m is greater than k. We can prove the other case in a similar fashion to this case. So, I leave that case to the students as an exercise. So, let us now say that I have that r is m minus k, r is m minus k. Okay. So, then let us say that, let us consider this inner product. So, psi of mn with psi of kl. So, this will be 2 to the power r by 2, integral from negative infinity to infinity, psi of t times psi of 2 to the power r times t plus s dt. Okay. So, what I have done is I have replaced r m minus k by r, where and now I have introduced a new variable s by 2 to the power r times n minus l. So, I have simplified my inner product using this new variable s. So, notice that since psi is my Haar wavelet, so psi is my Haar wavelet. So, psi is the following characteristic function. So, this is from half to 1. So, it is a Haar wavelet. I have that, let me call this integral as 1. So, 1 is identical, is equal to 0 if and only if we show that the following integral from 0 to half of psi of 2r t plus s dt minus integral from half to 1 psi of 2r t plus s dt, that is equal to 0. If I show that these two integrals are, well, the sum of these two, the difference of these two integrals over this range is 0, then I know that due to the fact that it is multiplied with this following characteristic function, I have already shown that over this infinite limit, over this infinite integral, this one integral defined by 1 is 0. Okay. So, showing 1 equal to 0 is equivalent to showing that this is equal to 0, okay, because the way we have described my wavelet psi, my Haar wavelet psi. Okay. So, let us look at these two particular integrals. So, my integrals are integral from 0 to half psi of 2 to the power r t plus s dt minus integral from half to 1 psi of 2 to the power r t plus s dt. So, notice that if I were to replace x by 2 to the power r t plus s, I see that this particular integral is now integral psi of x dx, and notice that the new limit that we have is now from, so when I plug t equal to 0, the lower limit is s, and when I plug t equal to half, the upper limit is a, where a is given by s plus 2 to the power r minus 1. Okay. Similarly, in the second integral, I see that the integral changes from a to b psi of x dx, okay, where my second value of the coefficient b is s plus 2r. So, all I have to show is that these two integrals, the difference of these two integrals over this limit is 0. Okay. So, but notice the following. Notice that my interval 0 1, it lies both in this limit s a, and it also lies in the limit a b. Why? Because notice that this particular integral is integral from s to s plus some value 2 to the power r minus 1. So, I can appropriately shift this integral from 0 to 1, shift and scale. So, we can shift and scale this integral so that it becomes an integral from 0 to 1, and similarly notice that this particular integral is integral from a to a, well, it will be a to a plus some factor which we can evaluate, and again this integral can also be shifted to 0 to 1. Okay. So, notice that 0 to 1 is a support or a subdomain of both these intervals, and I know that psi in this interval will well, I know what is the definition of psi in this interval. So, in this interval 0 to 1, let me call this integral as my 2 in this. So, what I have is the conclusion that 2 is going to vanishes, that is this integral from s to a minus the integral from a to b is 0, because it contains it can be appropriately shifted and scaled to have the integral from 0 to 1, and from there I can show that due to the definition of psi, the integrals individually they are 0. Okay. So, what I have shown here is, if m is not equal to k, then the inner product of m l, the inner product of m n with psi of k l, it is identically 0, or hence I have shown that psi m n, the way we have described my discrete transform, this is orthonormal. So, this is orthonormal, and hence this nicely defines the discrete Haar wavelet basis. Okay. So, that completes my discussion on the description of discrete Haar wavelets. Okay. So, all we need to see is whether those wavelets are orthonormal.